So what we're going to be talking about now is lipid synthesis. Now I've broken lipid synthesis up into a number of different videos. So this is part one. It's going to be fairly brief, and I want them to all kind of be brief. And so the first thing that I want to bring up is this is basically our cell, and this is our mitochondria. This captures everything that we've been talking about this semester. We've got glucose being imported in the cell, and sorry, this is all taking place, sorry, this is specifically a liver cell. We've got glucokinase that phosphorylates glucose, and we go on all the way to pyruvate that's imported in the mitochondria and so on. Now, what I'd like to draw your attention to first and foremost is where we are going to be compared to where we have been. Most recently, what we talked about was beta oxidation. Beta oxidation is taking place inside the mitochondria. Now, I'd like to contrast that with our fatty acid synthesis. So our fatty acid biosynthesis is taking place outside of the mitochondria in the cytosolic space. So we've got this division of these two processes. That's helpful because, well, we wouldn't want to have two reciprocal pathways going in the opposite, we wouldn't want reciprocal pathways operating in the same space, because if you're trying to build up a fatty acid while you also have beta oxidation taking place, it seems like it would be a little bit more complicated to regulate which process is on, which process is off. So in this case, we're looking at a fatty acid biosynthesis in a liver cell. So this right here is our display of our two reciprocal pathways. We've got beta oxidation, which takes place in the mitochondria, and we've got fatty acid biosynthesis, which is taking place in the cytoplasm, or the cytosolic space. Now, for each of these, I'd like you to kind of visualize them starting in different positions. So when it comes to beta oxidation, we're starting with a fatty acyl-CoA, and when it comes to fatty acid biosynthesis, what we're doing is we're starting with a fatty acyl ACP. Now that ACP we're going to go into a little bit more, but for the time being, ACP stands for acyl carrier protein. So that protein is, I would say that it serves a similar function as glycogenin. If you remember, glycogenin was the molecule that served as your kind of primer for synthesizing glycogen molecules. It had a tyrosine residue that kind of mimicked a glucose molecule that you could build these long polymers off of, or these long polysaccharides off of. Now, that's what the acyl carrier protein is doing. It's serving as kind of the foundation to add additional carbons onto it. Now, you have the acyl carrier protein serving as that acyl group carrier. Now, in a similar way, fatty acyl-CoA, coenzyme A is acting in a similar manner to be the acyl group carrier. So you have these long fatty acids that are basically conjugated to something. In this case, we have a fatty acid that is linked to a coenzyme A molecule, and over here we have a fatty acid, a starting fatty acid, an FA, that is bound to our acyl carrier protein. Now, I'm going to focus over here on the synthesis standpoint, and what we're doing is, first and foremost, is we are adding a malonyl-CoA molecule. So malonyl-CoA is 3 carbons, and so whenever we are adding that molecule, well, 2 of the carbons are added to our fatty acyl ACP. 2 carbons go to FA-Acyl. CP, the 3rd carbon is released as carbon dioxide. Likewise, that coenzyme A is also released. That allows you to form a beta-keto-acyl ACP molecule. Now that beta-keto-acyl ACP, which, just so everyone knows, I'm going to be getting into this in quite a bit more depth in the next few videos, but beta-keto-acyl ACP serves as your molecule that you can then undergo an oxidation reduction reaction with the help of NADPH, generating NADP plus and 3-dehydroxyacyl ACP. So this is still bound to that acyl carrier protein. You're going to remove some water, enoyl ACP is produced, then another oxidation reduction reaction where NADP plus is generated, and ultimately you're left with fatty acyl ACP. Your additional 2 carbons have been added to form that fatty acyl ACP. So when it comes to elongating a fatty acid, well, that elongation step takes place right here. That very first step, when you form that beta keto acyl ACP, you've added the 2 carbons that you needed to add in order to make that elongated fatty acid. Now, subsequent steps 2 and 3, 2, 3, and 4, basically what you're doing is you're just kind of cleaning up the mess, cleaning up the remnants of that, or the aftermath of that. But like I said, we're going to be getting into this quite a bit more in the not too distant future. If you compare that with fatty acid oxidation, or your beta oxidation, well, your 2 carbons are not removed until this last step right here, and those are removed in the form of acetyl-CoA. But the key is that these synthesis and beta oxidation are processes that are basically dealing with the addition or the removal of 2 carbons at a time. All right, now this is to contrast our 2 molecules. So what we've got right here is this top structure, which I'm going to switch to the highlighter. Our top structure here, phosphopanthene prosthetic group of the acyl carrier protein. We've got this group that is basically the exact same right here, that is hooked up to the acyl carrier protein, similar to how it is hooked up to the coenzyme A molecule. Now, one thing that I'd like to draw your attention to, whenever we talked about glycogen, we talked about a particular or a specific tyrosine residue. That tyrosine residue had our ring. Oopsies, that's supposed to be a 6-member ring. Excuse me, a hydroxyl group. And it was here that we added our remainder of our ring structure. Or sorry, we added our first glucose molecule that made that glycosidic linkage and built on from there. Now, in a similar manner, I'd like you to recognize this is a serine residue. Or sorry, well, this is actually the serine residue right here. A serine residue is CH2, and I'm just drawing the R group. Here's our alpha carbon. Then we've got an OH group. Now that group can be phosphorylated, or what you could ultimately do is add a phosphopanthene prosthetic group to it. And that enables you to go on to basically synthesize a larger fatty acid. So they're similar to one another. They both have this prosthetic group it's a prosthetic group in the top one because of the fact that it's conjugated to or bound to a protein, whereas in the bottom, it's just a functional group. That functional group is identical, and that serves as kind of your foundation for fatty acid biosynthesis, and it serves as kind of your primer for breakdown. So in addition to these processes taking place in different parts of the cell, you've also got these fundamental differences in your kind of starting material. So the acyl carrier protein versus the acetyl-CoA molecule. Now, this is your overall flow chart. Like I said previously, we've got an acetyl-CoA molecule, or an acyl carrier protein molecule, and malonyl-CoA. Now we're going to look at this top part right here a little bit more in more depth in the next few slides. But it's in this first enzyme, this beta-keto-acyl ACP synthase, where we've added the 2 carbons from, the 2 carbons from malonyl-CoA, or malonyl ACP. So it's these carbons that I'm drawing a circle around right here that actually get added. And so what happens is we have these multiple enzymes that are basically going to serve as the primer for the formation of this aceto-acetyl ACP, so that we can ultimately go on to synthesize and, well, get a longer fatty acyl carrier protein molecule. All right, well, that's all for the first intro to fatty acid biosynthesis, and we'll continue on. Thank you very much. Have a good one.